Okay, I'm here, I think.
Yeah, you are live. So let me just tell you briefly um, that there may be questions in the chat box, or there may be some people who want to ask by unmuting. So except for the speakers and session chair, others cannot join directly. So somebody has to kind of, if they want to really unmute and ask a question, then we have to let them in from the audience. But for example, session chair or a speaker or whatever, they can of course directly unmute and ask questions to you. So you won't be able to see anything. It's usual stuff in all the platforms that you might have been presenting over the last 2 years. So yeah, but hopefully yeah, we will help you with navigating the presentation as well as the Q&A part.
No problem. And of course, if there is any other question that I didn't see or didn't answer, just email me. I'm always.
Yeah. I think once you get off your presentation and you get into the audience or whatever, so basically, let me say you can stay live, or you can when you click. If you now you will see a red button on the top right, go backstage. So you can go backstage and you can still listen to everything. So you don't lose anything. You kind of can see the Q&A chat box if there are some questions, because obviously we cannot take all the questions due to the limitation of time. So you can continue, answering those questions, while you're even in the backstage. Only thing is, if you have a question for the speaker, then you cannot ask, I guess, from there. But you can, since you are a speaker, so you have privilege. So you can again go live and join panel, and then you should be able to unmute and directly ask questions. Yeah, I mean, if you want to chat, I mean, put in the chat box or raise a hand, whatever you can do. But otherwise, you can directly do. But otherwise, if you even go backstage, there is no issue. I mean, you can still hear. Yeah, but obviously, when you are presenting, then you have to be on the panel along with the session chair. Yes, Arindam.
Okay, good. Can you hear me?
Yes, yes. I can hear you. I can see you. So we are
Wonderful.
all set.
I could
The
not.
first speaker is here. Igor.
Yeah,
Arindam.
I'm here. I'm here. Just turn off the camera, but I'm here.
Oh,
Yeah.
hi.
Yeah.
Good.
I just want to check with the backroom team. So, I mean, you guys, do you want to give a brief, overview so that people can navigate without a problem, like for, speaker, participant, or session chair? Any of you in the backroom?
There's one problem. I can't see how I can switch my video off. I mean, maybe I just have to do a little bit of searching, but
The video on off is at the bottom of the screen. There is a camera.
is it? Bottom of the screen, there's a camera. Ah, I think I got it. It's sort of, oh, I think I got it. Yeah, why not? Check.
Yeah, so these are basically for, so the hand raise option is actually, if you go to Q&A,
Yeah.
not Q&A.
How do I don't know. Igor's screen might have a camera, but mine doesn't for some reason.
Huh.
Doesn't have a camera at the bottom. It has a.
I just have the thumbs up. That's it. Nothing else.
If you join the panel, then you might can see. I guess you have joined, sir. Is
I
there
have
any button you can see join panel?
What do you see on top of your screen? Do you see go live or go backstage?
Go backstage. It is there and go
Okay, then
backstage.
you're
That means
already
you are live.
Yeah.
You should be able to see these mute, unmute, and camera on
Your
off at the
screen
bottom
buttons.
next to your
Okay.
hand. No.
No,
So what is showing next to the thumb?
nothing. Actually, there's nothing next to a thumb. That's a problem.
Oh,
I've got 2 more
Interesting. It's
minutes.
okay. I can speak and they can look at you. No problem.
Yeah, I think we will start, and then you can give me the mic and the. I mean, at least, of course, mic is working, and you can see me, so the video is working as well. But how do I get rid of it is the question.
Anindam, can you try going to backstage once?
Yeah.
Yeah. So I don't see him anymore. You came back again, right?
Yeah, I came back again. They found nobody there.
So basically, then if you want to kind of make yourself invisible, then you can go backstage, since your camera on off is not working.
Okay,
So
fine.
that's one way. That's one way. But we'll try to find out why this is happening in particular for you.
Sure.
But then if you have to ask a question or whatever, deal with the audience or alert the speaker or something, then you have to go live again and then alert. Okay. So I think I will hand over the floor to you, Arindam, and then you can do the introduction and chair the session.
Okay.
So let me welcome all of you to this first show of this Spark workshop on low-dimensional material and topological materials, light matter interaction. And this first session will be chaired by Professor Arindam Ghosh, professor in the Department of Physics, IISc, and himself an active researcher in this low-dimensional material and light matter interaction as well. And so Arindam is 35 plus 5, and you can alert the speaker accordingly. I mean, you want to give a buzz at 30 or something, that's up to you, but it is 35 plus 5 for Q&A. And we can help you if there are questions in the audience. You can see in Q&A or discuss, but if you can't find, or if there is somebody wants to unmute and ask a question, I think the backroom team can help and they can coordinate with you. No issues.
Good. Great. Thanks.
Okay, then. It's all yours, Arindam.
Okay. Actually, Igor, can you just share your slide if you can, so that we can get started?
Can you see it?
Yep, we can see it. You're all set to go. Okay. It's still not 15:30 according to my local time, so I'm just waiting for about a few more seconds, and we can get started.
Sure.
Because I'll then give you a buzz at 30 so that you can finish by 35, and then we can have the questions.
No problem. So yeah, give me a buzz at 30 and we'll see how we go.
All right, wonderful. All right, good. It's 15:30. All right, welcome everybody for the first session of the Spark workshop. And our first speaker is Professor Igor Aharonovich, and from AR Systems at the University of Technology, Sydney. And Igor is going to talk about quantum nanophotonics with hexagonal boron nitride. Igor, the floor is all yours.
Thank you very much. So yes, it's a pleasure to be online, but with you. And good evening, morning, wherever you're joining. So it's a nice evening here in Sydney. So maybe actually I would start by kind of showing that we are actually relatively close between India and Australia. And so in Sydney, we are here somewhere down on the right, and it's we have a very small campus, actually, only a few buildings, but very close to the bridge and the Opera House. So I would like to basically extend this opportunity to invite you all to visit once the pandemic is over, hopefully this year. Okay, so today I want to talk about basically quantum nanophotonics with hexagonal boron nitride, and just to provide a very brief motivation, we want to find the best hardware system for the quantum internet. So we really want to think about interconnecting different nodes, and we would need some sort of single photons to communicate between them, and of course some access to a memory. There is a weird echo. Is that on my side, or?
It actually, unfortunately, Igor, I had to come back. It might be echoing with mine. So I'm going to go backstage. But if I go to backstage, I can't hear you, unfortunately. So,
okay. Okay, that's no problem. Maybe, yeah, you cannot unmute yourself. Okay, that's fine. We'll go like that.
Let me try. You can continue, please.
Cool. So we're looking for hardware to basically develop this algorithms and this proper photonic quantum networks. And so one way to do it is, of course, to use kind of the best atomic memory you have, and this is a single atom or single ion. And there are beautiful works from the group of Rempe here just last year, where they interfaced two trapped ions by about 60 meters and built what's called kind of an elementary quantum network. Of course, you want to go to the solid state as well. So this is now about 2 years old, and this is the work from Derek England, who interfaced a diamond, carefully nanofabricated diamond resonator. So these are tapered waveguides, and every waveguide is hosting a single photon source or a quantum emitter or a qubit, and this is all integrated on the aluminum nitride chip. So basically the vision is kind of hybridize the systems and get the best qubits and interconnected with the best optical interconnect so that you can have photonic quantum information on chip. So our effort is predominantly focused around the single photon sources or the quantum light sources. And, if you look at the library of single photon sources, actually quite a few of them, defects in carbon nanotubes, and of course quantum dots and molecules and color centers in solid. We are very interested in this system in particular for many reasons, but one of them that is a very practical one for students to work with. And this is because it operates at room temperature, and you can have your diamond or your hexagonal boron nitride or silicon carbide holding it in your hand, and then if you drop it by accident on the floor, you can pick it up, and the quantum system is so robust operating at room temperature that you can put it back under your confocal microscope. So just to give you kind of a very one slide what a quantum emitter is. So typically a quantum emitter is an isolated quantum system. You can think about it as an artificial trapped ion or artificial trapped atom in solid. And when you talk about, let's say, bound states or quantum dots, you have some sort of detuning from your conduction and valence band. So these are the typical quantum dots, gallium arsenide, etc., and they operate at cryogenic temperatures. And defect states have a very deep ground and excited state within the bandgap, and these are your defect centers in boron nitride and diamond and silicon carbide. And so to know whether you have a single photon source or not, you measure what we call a Henry-Brandon-Twist measurement, or an HBT, or an anti-bunching curve. And you simply split your light between two detectors, and you measure start and stop measurement correlations, and you have a dip here at 0 delay time. And if you have this missing count rate here, or a dip, that means that you have a single photon source. And so you will see quite a few of those dips and G2 functions, as we call them, in my talk. So I thought I would just put a slide here to emphasize. So we're interested in these systems in the defect system, and for that, of course, you need a wide bandgap material. And so if you look at this diagram of bandgap as a function of your cell lattice, you will see that there are a few systems up here with a very high bandgap. And of course, large bandgap is needed because you really want to have your ground and excited state very deep within the band. You don't want to interface with any of the conduction or valence bands. And so here, diamond, of course, studied for many years. Aluminum nitride is here as well, but also HBN. And in this regard, HBN is unique because that is the only material out of this entire library that you can exfoliate into a two-dimensional system. And so our group and many other groups realized that kind of a few years back, and started to study this hexagonal boron nitride for quantum photonic applications. And so really, HBN or 2D materials, they offer interesting prospects. Well, of course, you can do what's called twistronics, and I think in the field of condensed matter physics, and also I'm sure in topology, this is probably one of the more fascinating aspects. You can also think about valitronics with different transition metal digital coordinates, and of course, simple device integration, where you can fabricate a cavity from any material you like, and then position your two-dimensional system on top to achieve coupling. And so really, these 2D systems, how should I say, they bring accessibility to nanophotonics research, because you don't really need to grow very high purity gallium arsenide or diamond anymore. You can simply exfoliate and then assemble in a Lego style your devices in pretty much every lab around the world. So indeed, this is why this field of 2D materials is really growing kind of exponentially. Okay, so today I'm going to talk about defect engineering of these single emitters in HBN, and then hopefully, if we have some time, to talk about photonics and some spin properties. Okay, so as I mentioned, quite a few groups actually started to study these materials, this hexagonal boron nitride. And the beauty of it is that you can really engineer these emitters in many different ways by positioning HBNs on pillars and doing plasma processes and implanting. And very recently, also kind of indenting with AFM tip. And one very interesting work here from the group of Stefan Hoffman. So they made an array of HBN emitters, and they did it by basically taking an HBN flake with a very high density of emitters. You can see them here. And then encapsulating it with pristine HBN and patterning graphene. And so because graphene induces non-radiative energy transfer, essentially you're killing the emitters everywhere where there is no aperture. And everywhere where there is an aperture, you basically have an emitter, and you can see it here. And some of them are, of course, single photon sources. So you can see this beautiful emission engineering is possible purely because you're working with these atomically thin layers of boron nitride. So one question remains unknown, and this is, of course, what is the source of this boron nitride? And so we started to tackle this problem by growing our own material. And you can grow it fairly easily by just mixing up precursors of ammonia and argon. And so you can grow HBN on copper flakes. So this is basically 1 centimeter square copper film with HBN on top. And you can see here histogram of emitters. So every emission looks like that, with a very strong zero phonon line at around 570, 580 nanometers, with a very nice G2 curve. And so, this sample has millions and millions of emitters, in principle sufficient to graduate a generation of PhD students that would do experiments on these emitters. So this is a spectral control, so we can now engineer them at the right spectral position. And to achieve kind of also lateral control, you can then grow them on pillars. Here I just want to emphasize straight away that we are growing directly on the dielectric pillars. This is silicon oxide. And this is important not only because you can achieve spatial localization, but you can also then try to grow in an actual photonic devices. So for example, if you make a photonic crystal cavity or a macro ring or macro disc cavity, you can then grow your HBN directly on top. And so we played around with the size variation, and you can see that basically for 700 nanometer pillars, you can get very nice emitters. So every pillar has an emitter. and most of them are also single. So you can see here this histogram of G2 function as a function of pillar. And so this is nice not only because you have one emitter per pillar, but they're also bright, and you can actually go back to the same pillar location again and again if you are wanting to do more measurements. So again, you can do cool experiments with that, and I will not spend much time. This is really for those of you who are entering this field. So these are just preliminary experiments of strain tuning and electric field tuning. And this is simply by taking exactly the same HBN as we grew here or on copper in the previous slide and transferring it, for example, on PDMS or on ITO and applying voltage or just simply straining. And you can see that this behavior is actually quite phenomenal. You can really strain by about 20 nanometers or so. And I remind you that this is a single defect, which means that we are studying a single atom in solid at room temperature, and we manage luminescence controllably by about 20 nanometers. No other system, including diamond silicon carbide, can give you that on a single photon level. So these results really are very cool, and this is probably the best sensor you can ever imagine for your strain measurements. Okay, so the question is, of course, what is the defect? And this is a curiosity system, and being on this interface between materials science and quantum optics, it's really an interesting one. And so initially, we thought to basically kind of try to do some modeling, but we're not experts. So we started with carbon, and carbon was...
Sorry, just a quick comment, Igor. If you go to the bottom of your screen, if you click on hide, that because certain things are okay. Thanks.
Yep, there was nothing important here. I hope. Okay, so we were starting to look into carbon as a potential impurity into HBN, and the reason why we looked into carbon is because of a few works. This is by the group of Andrius Salkauskas that proposed that carbon is the responsible emitter in the UV range, and so what we did is, and you can ignore the details, I will just guide you through this table. We decided to partner with people that can grow wafer scale HBN by using MOVPE, so it's a molecular organic epitaxy method, and MBE and other methods. And what we see that we saw increased luminescence intensity with an increased carbon doping. And basically everywhere where there was carbon, there were emitters, and where there was no carbon, there was no emitters. And so this increase in luminescence is actually important. So you can see it here. As we went from basically 0.5%, we saw almost no emission. And as you increase your carbon doping in the growth to, let's say, about 2%, you can see this beautiful line shape, which resembles our emitters. And it's important because you can increase it linearly or controllably with the doping of carbon. And so then when you get to this 0.5%, you can employ a confocal microscope and then basically reproduce this very nice zero phonon line with a phonon sideband and measure an anti-bunching curve. And so when you study new quantum systems or new optical defects, it's very important to actually resemble the optical features of a single defect with an ensemble, like with the case of NV center and diamond. And so this is a very strong evidence that we have a carbon influence in our defect. You can do, of course, ion implantation. So this is an implanted carbon sample, which shows exactly the same lines. If you anneal the system, which means that you let the ions or let the atoms in the crystal to diffuse, you see again the same ensemble measurement. And if you do a control measurement of oxygen or silicon, you see very broad emission at the IR range, which is nothing to do with our single emitters. I will talk about this emission towards the end of my talk. So the last, of course, kind of proof of principle is dose scalability. So you can increase the dose from 10 to the 11 to 10 to the 14, and you can see this number of bright spots which correspond to your single emitters increasing dramatically, and you can repeat the same experiment again with oxygen and silicon and basically see no emission at all. So in this regard, if it walks and quacks like a duck, it's probably a duck. And so the assumption now that we do have all the emitters in HBN the single emitters in HBN are carbon related. And in parallel to our results, there were a lot of theory works coming out. And in fact, most of them are still in archive. I don't think they were actually published just yet. And they actually confirm exactly the same line shape as we measured experimentally. And they modeled this C2CB or C2CN, which means that it's a carbon trimer within the HBN lattice. And they have this emission right around the 1.6 eV, which is around the 650 nanometers. And actually, this trimer is also a very strong supporter of our implantation results. And here I would like to spend a second to explain it, because if you are familiar with, for example, diamond or silicon carbide, you would probably know that it only takes about 10 to the 11, 10 to the 12 nitrogens to get single emitters in diamond by implantation. But in our case, you really need to go to higher doses of about 10 to the 14 to get a meaningful density. And so this tells you that the defect is actually quite complicated, and this carbon trimer is actually supporting it, because you really need 3 carbons to see only one defect. So again, I mentioned there are other works as well that explain that there are some spin-dependent transitions, but I think the community is overall converging on these carbon trimers for this visible defects. Okay, so what can you do with them then? Well, so one thing that we did is we did some tuning, and I showed you already one slide on electrical field tuning and strain tuning. And here, back in the day, in 2019, already 3 years back, we also put electrolyte on top of this HBN because it's a 2D material and we can shift it. But what we did recently is try to really dry up the system and to do things electrically. And the results were actually quite surprising. So we made a very simple vertical heterostructure here with our HBN emitters layers and a capping layer and a graphene on top. So you can see it here. And what you can see then is there, if under 0 voltage, you basically see no luminescence. So under 0 volts, no luminescence. But as you turn the device on, a very low bias, only 4 volts, you can see that you can modulate the emission on and off. And actually, you start to inducing emitters. Okay, so this is not electroluminescence. Okay, so the laser is always on. But the laser is on with 0 volts, you see no emission. But the laser is on with 4 volts, you start seeing a very strong emission. And of course, it's a single photon source. So we looked into this more details, and you could see that when we turn on the voltage, actually the rise time to see the luminescence is very slow. It's about 80 milliseconds, but the bias off is about several tens of microseconds. So you can see that the mechanism between the on and off is different, and I will come back to this in a few slides. And when you apply negative bias, you see very fast on and very fast off. So that already tells you that the on and off is that the positive and negative biases induce different mechanism for this emission. So we looked at this further. So you can see here, and I'm sorry, this is a bit of a busy slide. So when you cool the system down and you induce a lot of ensemble of emitters, you can see that at 0 volts, 0 bias, there is almost no luminescence. Okay, so this is as a function of spectrum. There are many defects here. So every line is basically an emitter. And as you increase your voltage, you will see that the emitters will turn on and then off again. So here is a good example. So you'll see an emitter here turns on at 10 volts and then off again. And here turns on and off again. And here on and off again. And on the negative bias, you have basically a monotonic increase. So you turn on and it slowly increases and never goes off. So there were some similar works on, again, in diamond a few years back that reported a similar effect, not exactly the same. And so we looked at it in a bit more details and tried to come up with a model. And this was with the help of Alistair Stacey and Nicholas Dachuk from Melbourne. And what you can assume here is that, again, remember we have an HBN defect with our emitters and then a cap layer and then a graphene on top. And so our emitters are lying somewhere here below the Fermi level of the system, and about 2.3 eV before the vacuum level. The conduction band lies about 2.3 eV before the vacuum level. And so remember that we're working only with a green laser, right? So it's 532, so it's exactly enough to get to the vacuum state. So what is happening? So in principle, we can take the same level, the same energy system from these carbon emitters, and we can actually put them or superimpose them here. And so when we switch to positive bias, there is a band bending upwards, and we increase the bias, there is even higher band bending. And what is happening is that at some point, you shift from your transition level from 0 to -1 or -1 to 0. But as you increase the bias, you actually cross a second charge transition level. And so this explains why under 0 bias, you have no emitters. Under low bias, you have some emitters that are turning on. And under very high bias, you shift them off again because you're going to a different charge state. So remember that this is quantum systems that only operate at one specific charge state, for example, 0 or -1. And when you go to the negative bias, obviously you're not going to cross anything anymore. But what happens here is that, again, we apply 2.3 eV, which is the green laser, and you generate hot electrons because the junction is very, very small. It's only several tens of nanometers, and they can then recombine on your emitter level. And of course, as you increase the negative bias, you increase the recombination rate, which makes the defects brighter and brighter. So one proof that this mechanism is actually working is the difference in rate. So of course, this defect-induced luminescence will be very slow, and this fast electrons or hot electrons will be very fast, exactly as we see in our rates that I showed you a slide ago. And the second proof is, of course, if we now turn the excitation wavelength to 600 nanometers, so much lower than 2.3 eV, we're not going to see any of these defects. And so we did that exactly, and we see exactly that. So here is an emitter, for example, emitting at 710 nanometers that is on at very high biases. And as we change the excitation laser to 600 nanometer, exactly at the same confocal spot, looking exactly at the same system, we actually see absolutely nothing. And so this is just the Raman line of the 600 nanometer excitation. So this basically proves that there is this different excitation mechanism from these defects, and trying to understand these dynamics a bit better. So why did I spend about 5 minutes or 10 minutes describing this? Well, actually, it can be quite useful. And so here, once again, we're learning from our predecessors. And so this work was published by David Avshalom's group. And what they saw in silicon carbide is that if you're just doing photoluminescence excitation, so resonant excitation, under zero field, you have all these charge states. And of course, we see the same thing in HBM. But when you apply a bias and you create a depletion level and you really get rid of all the charges around the defect, you can see a very narrow and beautiful line of about 31 megahertz. So this device essentially under negative bias should do exactly the same, because under negative bias, you should really push all the charges away from the defects and only your defect should recombine. And so we did exactly that. And so under minus 40 volts, you can now resolve on resonant. So this is off resonant with the green, you can get very narrow lines, but on resonant, you can actually resolve almost nearly Fourier transform limited lines. And so this is, for now, a very promising way to generate a nearly indistinguishable photons in HBM. So I should say that we've tried indistinguishable photons, they don't work just yet. There is some decoherence problem, but nevertheless, the lines are becoming very, very narrow. All right, so I will shift gears a little bit, and I will show you some results from our integrated photonics efforts. So now we have the emitters, so we really want to integrate them with cavities and structures. And so here, of course, there are many questions of how to do it. So initial results were done on bulk HBM, so we can exfoliate and we can know the thickness based on color, and we can pattern photonic crystals. And so these are the initial results from almost 5 years ago now. On and off cavity, you can see a mode here, a photonic mode, but of course, very low quality factor. So then you switch your design from a 2D to a 1D system. And so this is a 1D photonic crystal. The quality factor is about 2500. And here you can already tune your emitter into the cavity mode. So you can see here being tuned into the cavity just by condensation. Now, it's interesting here that you can do all these measurements at 70 Kelvin. You don't need to cool down to 4 Kelvin really, because the emitters are already narrow and the cavities modes are narrow. So unless you're really interested in unless you have a particular reason to go to 4 Kelvin, you don't really need to. Then you can do all the tuning experiments at 70K and really measure Purcell enhancements and lifetime changes, etc. And so really this is a great advantage over kind of a standard quantum dot system that really you need to cool down to about 4 Kelvin. So you can also pattern monolithic waveguides. So not only photonic crystal cavities, you can also do waveguides. So here there is a waveguide coupled with a ring resonator and a beam splitter on chip. This is all done from a monolithic HBM and a beautiful tapered waveguide. And this was just on the cover of SES Photonics, I think a few weeks ago, or no, in October actually already. Time flies. Okay, so of course, because we're working with a layered material, we can take advantage of fabrication of other systems. So we can fabricate cavities from silicon nitride, for example, and then so you can pattern your HBM, transfer it onto silicon nitride, and then etch down the system together with an HBN. This works quite well. So here you can see a silicon nitride photonic crystal cavity, nanobeam cavity with an HBN on top. Obviously, you cannot see the HBN, but it's there. So in an optical image, you can see it kind of. So this is without the HBN. It's a bit brighter. And this red is with the HBN. So you can see here the contour, the white contour. And it's important to show that the mode, the quality factor of both with and without is pretty much the same. It's about 3000. And so once again, you can then measure your Parcel enhancement, and you can find emitters right in the middle of the cavity. And so this is a coupled emitter, Parcel of about 20. Our main challenge with this approach is that the emitter is still blinking and bleaching, meaning that you go through the cavity and then the emitter bleached. So here's an example of a bleached emitter. So don't get me wrong, it's not all not all honey yet. So it's not all. There is a lot of research to be done here on how to make these emitters stable. All right, so this was kind of just a brief overview of integration. And so I guess in the last 5 minutes or so, I will just show you what do we do with the spin properties, because I guess a lot of research is focused on spin properties of these defects. And here the story was actually quite interesting. So initially, we had a collaboration with a group in Brazil on just what's happening when you irradiate HBN with neutrons. You get these beautiful pink crystals. This is actually a pink crystal. It's not a false color image. They actually become pink. And this research was done basically in the 70s. People irradiated with neutrons, and they saw this OBC and TBC centers with spin half. You can open any literature on HBN from 1970s. You will see these beautiful lines. And what we noticed that with high doses, we saw this new line. And this new line appeared with a spin 1, not a spin half. And when we looked optically, we saw this we saw this broad emission around 800 nanometers. Now, please ignore the peaks. So we realized later on this is just an artifact of the spectrometer. So it's just a broad emission. But what was important is when you do ODMR on this broad emission, you actually see a beautiful response. So these are basically showing ODMR, so optically detecting magnetic resonance. So you can apply magnetic field, or even at zero field, you can swipe your microwaves and see a very strong response here at about 3.4 gigahertz. And then you can apply magnetic field, and this line will split as expected from a spin 1 system. And of course, having an ODMR, things become very, very easy. You can then use the hyperfine coupling, and you can measure EPR and resolve this hyperfine and really prove conclusively that this is a boron vacancy center. So you can actually couple, you can actually count this hyperfine line. So this is from the nitrogen vacancy, and you can see it doesn't really fit. There are extra lines, but the boron vacancy fits very well, 1-to-1, and so this spin defects are boron vacancies in HBN. So you can see an illustration here of the spins. So it's the ground state splitting, as I mentioned, so it's about 3.5, 3.4 gigahertz. It has a metastable state, of course. Fluorescence lifetime is a bit short; it's around 1 nanosecond. And one of the most fascinating things about this particular defect is we still don't really know where is the zero phonon line. So you can actually cool it down to 4 Kelvin, and there is no zero phonon line appearing. So the zero phonon line transition is actually dark, which is unusual for color centers. So a lot of this work was done by Andy Gottschall in the group of Professor Vladimir Dyakonov in Würzburg. And so they also measured the coherence time. It's not ideal, of course, but somewhere around several microseconds. It's pretty much limited by the boron and nitrogen spins in your lattice. Now, what's cool about the system, again, is the fact that making it in a monolayer or in a few layers of HBN. And so because it's just a missing vacancy, just a missing boron, you can easily make them on demand. And so we made arrays here. Every spot here is an array. And there was also other people already kind of working on that as well. And you can make it with nitrogen beam or argon or xenon. And you can see this, we can induce this emission very efficiently. And then we can kind of bring both walls together and make a cavity out of HBN and then induce the boron vacancies right in the middle. So we made a bullseye structure, just the easiest cavity you can make from HBN. So you can see here an array of many different bullseye structures. And you can see here that you can tune the mode of this bullseye structure. And once you hit this resonance at around 800, the emission is enhanced and the signal to noise ratio of your ODMR contrast is improved a lot. So this is again from the Dyakonov group. You can see easily 6% contrast, and even the peaks are resolved in this ODMR spectrum. So it's really nice result. And so again, I just want to emphasize that this is basically giving you this optical spin access, which means that you can use it for sensing from magnetometry or for any other application where you need an optically active spin sensor. And it's at the 2D material interface. So it means you can really put anything on top and sense. And so, of course, this was quite an interesting the system, and so other people already doing quite nice work with it. So this is the work from Tong Li group in Purdue, and so they actually improved the contrast significantly. So if you put this HBN on top of your microwave strip to generate the microwave, you can actually get up to 50% contrast. Okay, so again, remember that for example, in NV in diamond, the contrast is only about 10-15%. Now we're reaching 50% contrast. Okay, so with the magnetic field resolved, so that's quite cool. And ourselves, we also tried some gap plasmonic cavity to enhance the emission, and we managed to increase it by a factor of 10. Not much, not as much as this typical gap cavities should give you. So the expectation here is to really go to about factor of 100 or so. So let me just tell you a little bit about the limitations of the system. So maybe I'll stay on this slide. So as I mentioned, we don't know the zero phonon line. Yep. So we don't know the zero phonon line, and we also cannot make them singles. So all these measurements are done on ensembles, and here you see that as we reduce the radiation dose, we really cannot get any single emitters. The emission simply disappears at some point. So the non-radiative transitions are very, very high. The rates are very, very high. So there are a lot of things to do with the system. But I think the fact that it's available at your fingertips pretty much will make it very interesting to study over the next few years. Okay, so I guess I will summarize and spend a bit more time maybe answering questions. So I showed you that we can engineer single photon emitters in HBN, and we believe that they are carbon related. And I showed you some very interesting electrical control of this emitter, something that we still don't completely understand. Cavity engineering and coupling to cavities. So we have some preliminary results on coupling, but of course, we haven't really achieved indistinguishable photons just yet. And of course, the kind of the most fascinating topic is the spin defects in HBN, and this is with Professor Dyakonov in Würzburg and other groups. So I would like to thank the group first and foremost. So this is from a barbecue a few months ago, so our annual barbecue. And of course, again, as I mentioned, once restrictions are out, you all welcome. So this was before social distancing forced here in Sydney again. And of course, our collaborators, so Dyakonov Würzburg, Alex Kubanek, and of course, Professor Watanabe and Taniguchi, Alistair Stacey, Nikolai Lechuk, and Professor Jagadish and Hotan from ANU. I think you're mostly familiar and know Professor Jagadish personally. And of course, Oliver Benson, Weibo Gao, and Paul Barkley and Marcus Doherty from ANU. And thank you for your attention.
Thank you, Igor, for a wonderful talk. You can hear me, right?
Yes, loud and clear.
Okay. So we have a few minutes for questions. There is one question in the Q&A, which I am going to read out from Amit Rajit. Can you please enlighten upon what are causing the blinking and bleaching hair, or blinking and bleaching hair? So
maybe the best slide to explain it is actually this. So probably this. So you see that when we work with HBN, the material is very not perfect. So we have a lot of grain boundaries, a lot of impurities within the HBN, and when we transfer, there's a lot of polymer residue and a lot of defects with the HBN. And so what we think is happening, because it's still an atomically thin layer, we basically ionize some other defects, and then there is a charge transfer to the HBN defect, and then they turn on and off. So all this blinking is basically from surrounding defect within the HBN. So we haven't really tried to work with large ultra pure crystals, which are available if you want them. I think that will probably be a bit helpful in the future, but it's from these impurities within the HBN.
Okay, so we have got two more questions. I think Sudarshan is asking, hello, Professor. Is there any particular reason for choosing hexagonal boron nitride, hexagonal structure of boron nitride? Is there any other structure that is tried?
So I'm not sure I follow. So in terms of HBN versus QBN, or in terms of HBN versus...
Probably that is the question. Yeah, I mean, is the hexagonal structure anything special, or...
Yeah, so yes, right. So HBN, the unique thing about HBN is that you can actually use it as a 2D system. So if you take any other form, let me go back to the introduction. If you take any other form of BN, you can't really exfoliate it into 2D. So HBN, like the hexagonal structure of boron nitride, is the only one that can be really exfoliated into monolayers or atomically thin systems. And so this is important because it really provides you ease of scalability. You don't, for example, if you want to make a cavity out of diamond, you need to somehow make a diamond membrane or somehow to make a diamond suspended. In HBN, you can simply suspend it over a silicon ridge and get it there. So it's really about kind of scaling up your system. That's the advantage.
Okay, great. The next question is from Sarthak Das. Can you comment on the detection part with 2D materials? I think it's a little broad question, so maybe you can just concise. What do you think?
Yeah, so we haven't done much. So there is a lot of effort with using materials like even WS2 and some tellurides to do detectors. So the main problem is the absorption. So the absorption cross-section of a 2D material is obviously extremely low. So if you manage to encompass this system into some sort of mirrors or some increased absorption, then of course it's possible. And different groups actually working on that. So there is a very nice work from, I think, the group on MIT, from Derek England, and I forgot who is the collaborator there, that they did demonstrate that graphene can be used to basically absorb almost nearly single photons at the IR. But at this point, I don't think in the visible range there is much work done on 2D material absorbers.
Okay. The next question is, will you explain the spin defect once more, and how is it connected to the bullseye cavity? This is also another question for Amit.
Yeah, sorry, maybe I was racing through it, so let me spend a bit more time on it. So basically the spin defects are defects where you can record your luminescence, and then when you apply your magnetic field, when you apply your microwave frequency, you can see a dip in luminescence. And so this is because as you excite your system, it can go through the metastable state or directly down to the ground state. And one of this transition is spin forbidden and one is spin allowed. And so because one is allowed and one is forbidden, and they have different rates, you will see a contrast in this ODMR, what's called ODMR. And so the reason why this is important is because it's a spin-dependent transition. It's very sensitive to anything spin related, which is magnetic or electric field. And so this is why this type of systems are very, very important. Now, how is it related to the bullseye? Well, so the problem with this particular system is it's very dim. So the emission here, it looks good, signal to noise ratio, but it's actually very dim and we cannot get to a single level. So we were thinking of how you can enhance this emission. And to enhance an emission, you need to make a cavity. And the simplest cavity is a bullseye structure. So a bullseye structure will give you a factor of 10 in emission. And so you can see it here that a pristine HBN, this is the red curve here, only gives you about 1,000 counts, and a bullseye structure gives you about 5 times more. So experimentally, we are only a factor of 2 away from a theoretical limit. So and then because we can make these spin structures in the middle of the bullseye, we can then basically again make an ODMR contrast much better. So you can see here it goes to 6%, and the more it goes down, the better the contrast, which means the faster you can actually do your measurements.
Great, thanks. I'll take one more question, and that is from Dr. Rajesh Vinayar. Is there any natural defect present in HBN, or we need to create them by using ion implantation?
That's a very interesting question. So originally, we found that single emitters occur naturally. You only need to anneal. So we took just commercial powder of HBN and anneal, and you have plenty of defects occurring naturally. The reason why they occur naturally is because HBN is grown under high temperature conditions, always with a carbon precursor around it. Even if the carbon is not introduced intentionally, it's always there, simply because that's how it grows. So you will always have naturally occurring defect in HBN. But the boron vacancy, this defect, actually will never occur naturally. And this is because the boron vacancy is diffusing at very low temperature, about 200 degrees. So what you need to do is you need to implant to create those boron vacancies, and then you do not need to anneal. So you cannot anneal. If you anneal at about 800 degrees, this defect will actually break apart. So these defects you will not see naturally, but all the others you will.
Okay. Yeah. Wonderful. All right. I think we are out of time. I just want to have one question for myself. Is what's the maximum brightness level that you have got with these boron nitride emitters? I mean, and does it depend on the thickness of the boron nitride layers? I mean, more than a monolayer.
Yeah. So the brightest emitters. So we now in the lab for the single emitters, we can measure routinely about 2-3 million counts per second. So those emitters here, So those typical emitters here we can measure about 2 million counts per second. So that's 2 to the power of 6, and that's without any photonic structures. If you use a photonic structure like a solid immersion lens or a cavity, you can get up to 10 million. So they're very bright.
Yeah. Okay. Good. Thank you very much, Igor, for a wonderful talk. And let's thank him with our claps, electronically, if possible. And there you go. Thank you very much.
Thank you.
Okay, so we come to our next presentation by Professor Jaydeep Basu. Jaydeep, would you like to share your screen, please? Jaydeep, are you there?
Can you see my screen share?
Not yet, but I'm hoping it's going to come. Yeah, I think I can see it in one corner. If you can make it full screen, please. No, it's just stuck at the corner.
Or you have to click on pin. If you on your screen, if you click on pin, it should.
Oh yeah, got it. All right. Okay, excellent. Okay, so our next speaker is Professor Jaydeep Basu from the Department of Physics at Indian Institute of Science, and Jaydeep is going to talk about light-matter interactions in plasmonic cavity-coupled quantum dots, single photons to long-range polariton transport, and spin momentum locking. Jaydeep, I'll give you a buzz after 30 minutes, and then you can wrap up in next 5. All right, floor is all yours.
Okay, so thank you, Arindam, and also thank you, Igor, for a very nice, very fascinating presentation. I had questions, but we can discuss offline. So today what we are going to do is going to show, I mean, you already got a very nice introduction to single photon emitters of a particular type, and some aspects of coupling to some cavity. What I am going to focus on here are different aspects using different emitter and different cavities. These are largely plasmon based. So before I let's see, something got messed up. Okay, I have to use this. So before I proceed, let me kind of acknowledge some of the collaborators who are involved in this work. George and Terry from Northwestern, Gary and Stephen from Argonne, Girish Agarwal from A&M, and of course the work done largely by student Ravindra. And of course, funding agencies, IUS-STF, we had a project here. We have a Spark, which is of course basically sponsoring this workshop, which involves Girish Agarwal, and there are 2 other partners, and you will hear them speak tomorrow and in the next session. So what I'm going to walk you through in the next 30 minutes, 25-30 minutes or so, is trying to show different regimes of coupling. So essentially, the talk is going to be about when you couple emitters from a single emitter all the way up to a very kind of a compact assembly or ensemble. What are the different regimes that you encounter, and what are the different phenomena that you can see when you couple with these plasmonic lattices? And I'll elaborate on what these are. There are broadly 2 of them. The one involved here, and these 3 aspects that I'm going to talk about are going to use a optical lattice of metal nanocylinders. So essentially, you can have basically 2 different regimes. So one is this kind of well-known mode where you take some plasmonic entity, metal, maybe silver, cylinder, disc, or what have you, and then you create an array of that, and also you basically create the array in a manner that there is strong coupling between interaction and strong coupling between these individuals. So individual plasmon mode and the field is kind of well known, I guess, to the audience. I don't have to introduce. But then when you create this this kind of array and they are coupled, then apart from the localized mode, you also create what are called the diffraction mode or the surface lattice resonance. And for example, if you do transmission measurement, then you can see this very sharp. The typical plasmon resonance would be broader, but the lattice resonance typically is very, very sharp due to this strong coupling. So so that's one, and you can vary the lattice spacing here, typically of the order of 400, and you can go even higher to larger separation, basically shifting this the position of this resonance to smaller wavelength as you increase the separation here for the lattice. Okay, you could the other type that that I will talk about here are these so-called metamaterial. I mean, metamaterials, I'm not going into the detailed introduction, but basically what I'm going to talk about are these so-called hyperbolic metamaterials, which have this hyperbolic dispersion, depending on the dielectric constant relationship as shown here. So you have this type 1 or type 2, depending on how. So you need one of these to be negative. In all the cases, in normal dielectric, it will be all positive. In this case, it will be all same. But here you have essentially anisotropy, but also you can have one of the components which becomes negative, for which of course you need to put in metals which will have a negative part in the dielectric, will contribute negative part in the dielectric constant. Now with these plasmonic nanoparticle arrays, there are a lot of studies in the last 7-8 years. For example, showing lasing with this, right? Or even there are studies where people have talked about Bose-Einstein condensation in this plasmonic lattice. So there it has been kind of widely studied, and there are a lot of other types of studies which have been done in these systems as well. So I'm not going into the details of these. What our interest is basically that to take one such an array, and this is something which is fabricated in the group of Terry Odom in Northwestern, and these are some sort of you can imagine that you can calculate a band diagram and you can have a dispersion relation as well, and different size arrays indicated here will give you different dispersions. The idea is, and you can see the resonances here for different lattices. You can see the larger lattice spacing, shifting the peak to the lower energy. So the idea is that if I couple the quantum dots, and the quantum dots in this case are the 2,6 CAD selenide zinc sulfide cap quantum dot core shell. They have very high quantum efficiency, and they have been used for the last almost 30 years or so. So very kind of well studied and well known. And the biggest advantage is that you can actually tune. So that's the biggest advantage of these emitters, that you can actually tune. So here you see for a particular wavelength, but you can tune it for even a given material, you can tune it over 100 nanometer or of that order. So you can tune it through size and to other methods, and so you can then use that and then play around with how it relates to this the resonance that you have, the lattice resonance. Of course, you also have the plasmon resonance. So the first part that I'm going to talk about relates to the work done where we are looking at a single photon emitting regime. So very dilute dispersion of these quantum dots on these plasmon array, and we are going to try to understand what's going on. So as I mentioned, that this is something that we have, and we have these individual quantum dots. They are separated so that they are not in kind of physical contact. And in most cases, when you excite, you can almost reach a regime where you're exciting maybe a single quantum dot. They are sitting and they are coupled to this plasmon array. So these are the individual kind of spectra. So this is for the quantum dot in, for example, if you take it in a solution, when you make it, these are overlaid basically. So this is not on necessarily on this one, but you can also collect data on this. So this is just to show that you can tune it, and it is nicely kind of maybe resonant with the surface lattice mode for the particular template that we use, right? So I'll show two parts, two results here. The first one is there we did time resolved photoluminescence measurement. So this is for these isolated quantum dots. If you take glass or some trivial substrate, so you get a nice kind of single exponential decay, and you can extract the time constant for the decay of photoluminescence of these quantum dots. So these are single quantum dots, but from this measurement you cannot tell. But the point is that you get a nice relaxation curve, which can be easily fit with a single exponential. When you now look at this blue curve, and I'll come to this. When you look at the blue curve, you start seeing that there is a deviation. There is a change because of the coupling to the LSPR mode. But then when you look at this regime or this system, you see a very strong change here, and you can see very clearly the existence of at least two distinct lifetime relaxations. So this is the same quantum dots on for example glass, and then when it is on this template, then you see that there is a very sharp change. So so this is so again, now we wanted to basically pull out some information. So we had the parameters, the data here. So we try to model this using a quantum mechanical treatment given here, and looking at the solution for this density matrix for the interaction Hamiltonian as defined here, and you can from this you can extract an effective decay constant for this interaction. This is of course in free space. and so the sort of the coupling parameter is what you want to pull out. So this is for the lattice resonance decay constant, or the LSPR decay constant. This is for the emitter in vacuum or free space, and this is the dephasing parameter. So with these quantities, one can actually try to extract, and this can give you, for example, the Purcell factor. So you can extract the Purcell factor from this and from this, and you see there is a significant increase in this quantity when you are extracting the Purcell factor. So this is for the only the LSPR mode, and this is for the when you have the lattice resonance which exists. So this is something which we could kind of pull out by doing this theoretical modeling. So I mentioned about single photon emitters. So what is the proof? So as I mentioned that if you zoom in here, you can see that on glass you see that it's almost kind of gone. So it's really very high purity single photons coming out from this emitter. So that is kind of very encouraging. And if you then look at so you see this kind of, if you wish, dip. So all of these are in the single photon regime. That means even when they are on the SLR, you still have them in the single photon regime, I mean, comfortably. But one notices that there is a slight increase here. Now, of course, people have commented about multiple possibilities, but what we have tried to explore by looking at trying to it's not as rigorous a model as we have here, but we try to provide some kind of a plausible explanation for what kind of explains this behavior. The other thing is that, as we had seen with lifetime, we also see this type of you can fit this to time decay, and you can extract this, and we see similar behavior coming out here from the G2 curve. So to kind of give a plausible explanation, this is a model which was developed, not a model, basically a plausible way to look at two things. So one, that there is an increase in this G20 value, and that can be, I mean, I'm not going into the details, but can be explained in terms of the probability of two photons. So this is a typical G2 measurement. So you have the two detectors, so, two photon detection probability kind of can explain why this value is not. So this is not kind of present on glass, but it's something that we seem to pick up, and then this could be related to the fact that you have this extended mode, the surface lattice resonance mode. But basically at this point we do not have the detailed model or the understanding of what exactly causes the one, but at least this is a kind of a possible way to look at. So there is a 20% probability, to cut a long story short, of how basically having one more quantum dot being signal being detected, so that can give rise to this behavior. But the other thing we try to look at is that there is this second component that we see, as I mentioned here, right? And so that is something that we believe is happening because it is, and it's very kind of it's there in both, but it's kind of strong in the in the presence of the surface lattice resonance. So we feel it's because of the indirect excitation of remote these quantum dots, which is mediated by this. So the lattice resonance, as I mentioned, is delocalized, unlike the LSPR, which is strongly localized. So that delocalized mode, it excites and it de-excites, but it's sufficient basically to possibly excite indirectly another nearby quantum dot, and hence you see a very strong presence of a second kind of relaxation. So in this case we have tried to estimate, but understand that these are the kind of the plausible model. This is not a kind of a basic quantum mechanical calculation to explain why this is happening. Those might be helpful, but definitely there are very clear signatures in either the lifetime or in the G2 measurement. So next, we go from single photon to a regime where we now try to vary the concentration. So these are whatever I mentioned here are all where, as I mentioned, completely isolated. Now, in the next work that I'm going to discuss, we now look at varying this. So you see, this is the AFM image of the pristine template. These cylinder arrays, as you can see. And then we can basically code them with this quantum dot. Now instead of one, we have a very compact layer, okay? And we can vary the concentration or the density or the thickness, what have you, so that we can do it in a very scalable manner. So we look at that and we try to explore whether there are what are these different regimes. For example, can we get into the strong coupling regime and so on and so forth. So, so that's something that I'm going to talk about. So, basically you also look at now, as I mentioned, that the advantage of the biggest advantage of these quantum dots are that you can basically tune them spectrally, keeping the material same. Don't have to do anything to the material, and you can see that you can span over a fairly large range. In this case, almost 300, 250, 300 MeV. Okay, and this is the lattice resonance, so you can come on resonant, you can go off resonance, so you can do tuning, detuning, so you can do that. So, so these are then the spectra that you measure on this template for these different quantum dots that I talked about, that having different intrinsic spectra. So these are, if you wish, they are measured external to this template. When you couple them, then this is what you see. You see the strong kind of splitting, which is indicative of the emergence of a strong coupling. And another signature is that when you basically try to plot this as a function of concentration, then they should show this type of scaling, the square root scaling, which is what we see. Okay, so that is good. So we are able to use concentration to now basically enhance this interaction. Now, if you see here, so this is it goes from what you see on glass, which is kind of a boring substrate, and then you keep seeing this the magnitude increasing as you increase the concentration. Now, is that all? So we kind of push this limit further, and this is now a comparative comparative data between what I showed here, that was the highest concentration, and when we pushed it, almost doubled it basically. So when you do that, and you see very clearly, you have something emerging here, the third kind of a peak or a mode which emerges. This is very, very clear. So now the question is, what is this? What is basically causing this one? So this we can think in terms of emergence. At least I mean, you need to prove it by other methods, but by and large, the scaling and several other things strongly indicate that these are polyatomic modes which are coming because of the emergence of strong coupling. Now, what is the third mode? That's not very clear. So essentially, then we look at the modeling of this in terms of an effective medium picture, right? And effective medium is in terms of the quantum dot, and this here represents the basically how. So as you increase the concentration, this increases the oscillator strength, and as you increase that, you start seeing this strong splitting in the imaginary part of the knee polaris. So there's a small detail basically in the analysis. These are taken as pairs for simplicity, but I guess the results would hold good, although the actual shape of these particles are disc-like. So you can see that scaling. But also, what is interesting is that one can calculate the density of states. Okay, using Green's function for the lattice resonance mode, you have the full dispersion in the momentums of states. Again, if you see that you have this feature emerging here in the density of states. So as you increase in this case oscillator strength, but in our case the experiment, you start seeing the emergence of this mode or this peak here, and this is around the region of the uncoupled modes. That's interesting. So you see these modes which can correspond to the upper and the lower polar branch, but you have something coming in between, which which is unique, right? So to look at that and to sort of understand that, we kind of do some more calculations, and we even do spatial dependent calculations. So this is indicated here, the positions around a particular plasmon element, a disk or a sphere, and you see for different oscillator strengths. So oscillator strength is small, and then it increases, and you start seeing this feature. These peaks are, and these positions are indicated here. So you can see that it is the absorption spectra is quite strongly dependent on the position, right? And so that's something which is indicative of the fact that it is not necessarily only a local effect, but it is also a non-local effect, and it involves the presence of SLR. It means it needs both LSPR and SLR. You are not able to decouple the effect individually, but it's very clear you need both. More so when the simulations were run with something else, which is titanium, with the same lattice, everything same, and you look at this same position, you see that you don't see this splitting at all, right? Except for this one position here, which is the one which has no LSPR, but it has this kind of lattice mode, a weak lattice mode. You see this. So in other words, the long story short, we see this that it is spatially dependent, and we say that this is something which is a collective behavior which emerges in the system, and that is one signature is that it emerges at the position of the original one, and that is driven by the SLR. Without the presence of SLR, you do not see this third peak emerging, and of course you need high concentration. So the enhanced absorption, because of the SLR mode, actually gives rise to the emergence of this collective emission mode, which has been observed in a different context in some other system. But here we are able to tune it, and also we are able to through the calculation show simultaneously the existence of all these different modes. So both these polytonic modes as well as this collective emission mode. Okay. So the next part here. So we have looked at this regime. So we have seen that what concentration can do. We have gone from single to the concentration dependent, and now we know in terms of the spectral behavior, in terms of the position dependence of the spectra, we have a good understanding, and we can see a new regime emerging as you push towards higher concentration. Now, is that all? So the question is that are these polytonic modes which we see are created, do they share or do they have some other properties? And that's what we wanted to explore. So this is something which is reported in this work, where what we did is actually essentially we excite this and we detect non-locally. So we basically excite and we detect non-locally, so the excitation remains fixed, and we can detect it with the excitation remaining here. So when we do that, what we observe is, of course, we see this kind of splitting as I mentioned earlier, and we see this scaling with square root of concentration. This is also modeled by a cavity QD model using this formalism here, including the QD and the lattice mode interaction for the Hamiltonian. But what we see in addition when we look at this spatial dependence is that as you go away from the excitation region, go away far away, very far away, significantly away from this excitation regime, we still see emergence of the evidence of these modes propagating. So that means this is something which seems to be propagating even far away from the excitation region, and that is something which is very interesting. In fact, when we actually look at the intensity, you can see that this intensity is actually going very far away. So if you do not have so again, to complete the story, if you put this on glass, this just drops up abruptly, as you would expect, because there is nothing outside the excitation region. Okay, exactly same, very compact, high density quantum dot layer, but it just basically decays close to the excitation regime. But when we look at it at these, you see them that they are increasing, and not only that, they also that the range up to which it propagates seems to be scaling with the concentration of the quantum dots. So this is the lowest one, and then this is slightly more, and this is more, and then this kind of keeps on increasing. So so this is quite fascinating because it's suggesting that because as we know that light of course can travel over long distances, but the excitons which are carried by the quantum emitters, they cannot. They have very short range diffusion that is well known. I mean, hundreds of nanometers maybe. But here, when you combine, you create these hybrid states, then they can actually, in some sense, retain the ability of, for example, the photons to travel long distance. But now you have a hybrid kind of mode, which you are able to transfer information over very large distances. So this was kind of model using this coupled dipole method, not in an exact kind of distance dependence, but as we can see here, that when we vary the concentration, then we see this kind of decay away from the excitation region, basically showing that it is scaling with the concentration as we see in experiment. So this is something quite fascinating, and there can be many kind of different directions or applications that you can think of, in which you can further explore this behavior. I mean, we have not looked at, for example, polarization dependence or many other aspects which can be combined or studied here. Okay, so basically in the last probably about 4 or 5 minutes, I'm going to slightly change gear and now talk about this aspect which has been kind of become quite widely discussed and researched in the last 5 to 10 years, basically where you can couple the helicity or the photon spin to momentum, basically enabling you to transfer light of a particular polarization or helicity in a given direction. So basically then you separate out or you create or generate light of a particular helicity or polarization, and that can be used for various quantum information processing and many other applications, quantum communication that you can think of. And there are several examples of this in different regimes. I'm not going to go into the details. So a lot of these use even metamaterials which are, for example, not in the visible but in the very kind of large wavelength regime, microwave and large wavelength regime. But there are some studies where this is happening even in the visible frequency regime. For example, this is somewhat from Sasha Lukin in Harvard, where they have shown this in terms of a visible frequency hyperbolic. So there is a meta surface, and basically they used the helicity of light to be transferred in different directions using engineering of these templates. Okay, 2D meta surface. So here our interest is somewhat related to these. That we don't necessarily use a meta surface, but we use this metamaterial. In particular, we use this wire type of metamaterial. As you can see here, this is kind of the top view, and this is the side view. So you can see these wires. So these are nothing but silver wires. They are grown in alumina matrix, and by varying the fraction of this metal in the background, you can control the permittivity both in the plane as well as perpendicular, and accordingly you can basically land up in one of these regimes. Okay, so this is not interesting. What is interesting is either you are here somewhere, or you can be somewhere here, depending on how you vary the fill fraction. The fill fraction is given here. So by simply tuning this, you are able to control the dispersion property of this material. And people have reported about optical topological transition when you go from an elliptic to a hyperbolic dispersion, how that basically significantly changes the density of states. So this is what is illustrated here, that for a particular filling fraction, you can go from a dispersion like this, spherical or elliptical, to a hyperbolic by using, so essentially as a function of wavelength. So here, for example, if you can see that the dispersion as the permittivity as a function of wavelength can go through a change from positive to negative, and then you have this transition happening, and because of that you have the decay rate, which can be controlled by the availability of this high k. Remember that the hyperbolic dispersion has this this large k modes which emerge. So you have these high k modes in addition to the normal of course vacuum, but you have the plasmon, normal plasmon. These are based on metals, so plasmon mode, but you also have this high k mode, which comes because of the emergence of this hyperbolic phase that happens around a certain wavelength. Okay, so we transfer these. This is how it looks like from top, SEM and AFM, and you transfer the quantum dot, the compact layer that you have seen earlier, and you see this is almost not visible, so it's completely covered. It's a very, very compact layer, high density. And so when you first of all, when you look at in terms of Fourier imaging, so if you look at on same thing, exactly same thing here, but not on this, but on glass, you don't see anything interesting happening, right? It's kind of very boring, no structure. When you put this on the metamaterial, you see this kind of strong ring, which indicates a particular preferential wave vector where there is intensity, which means that it's indicative of directional emission. And also depends on the thickness, interesting. That means how thick this we have a spatial layer in between, as indicated here, and the thickness basically will tune how well these quantum dots are coupled to these evanescent modes. So we will have this evanescent mode of this. These modes are evanescent, so you want to couple them. Otherwise, you can't access it from outside. So the spacer will determine how well you are able to couple to this evanescent mode. So this is one thing which emerges, and this is coming purely because of this template. Okay, the directionality comes from that. What is even more interesting is that when you look at,
we are out of time. Maybe one more minute.
Yeah, I'm almost done. So when you now come in with chiral excitation, then you see a very strong kind of helicity selection. So depending on whether you have left or right circular polarized, right, you see that there is a preferential propagation in a particular direction, and you can kind of pull out a chirality of the emission. And this was modeled. I'm not going to detail because we have run out of time. Detailed in terms of Boltzmann-Green function. Essentially, the long story short, what happens in this case is that you have a coupling in the evanescent mode, the coupling of the polarization, the longitudinal and transverse component, which generates this helicity. Remember that neither the hyperbolic metamaterial or the quantum dots have any intrinsic helicity. Okay, so it comes purely because of the coupling in the near field to this high K mode. And so basically, I will end by summarizing that we have shown that you can couple, single photon emitters. Then we have this, different regimes. You have the polarelectronic transport, long range, and then the last part, essentially, you are talking about directing chiral light in a particular direction. So you have the momentum and the spin, photon spin being locked, and that is achieved with none of these materials having any chirality, neither the metamaterial nor the quantum dots. So here, and thank you for your attention. Happy to take questions.
Thank you, Jaydeep, for a very interesting talk. I can see one question on the Q&A section. Let me read that out. Then others, I request to put out their questions on the question Q&A. As the question is from as it is seen that increasing emitter concentration increases the faraway PL intensity. So can it be possible that more increment in emitter concentration can almost flatten the curve starting from position of detection to anywhere farther. I don't know whether you understand the question, but it's not.
Yeah, I mean, so maybe, yeah. So the thing is that obviously there will be a limitation. So the first thing is that how closely you can pack these, right? So you can't pack them closer than their nearest neighbor distance, right? So there will be some, for example, shell or whatever. So that is where you will hit the limit in terms of how much you can increase the concentration. As far as increasing the, what happens to the transport, I mean, we don't know because we have not, artificially, gone increasing the oscillator strength to model it theoretically and see whether the length increases, or we have not seen any evidence of any saturation regime. So there may be practical limitations in terms of how to achieve even larger propagation length, but even at this point, the distance to which it is able to propagate is significantly larger than anything that that I think probably exists that at least I am aware of.
Kalipada is asking, how is a hybrid plasmon photonic cavity realized practically or fabricated?
Yeah, so the fabrication is normal procedure in the sense that you grow. So these are grown on transparent substrates. You can grow them on other substrates as well. But basically you pattern and you etch. So you grow these metal discs or cylinders, or you can in any other form. And so it's lithographic. So it's and these are optical lattices, so you can grow them without much trouble. So these are lithographically using then etching. This is there are a few groups in the world, but for example in Terry's group, I think they have kind of made it almost perfect. So they can tune the individual properties, that is the size, shape of the individual disc, as well as the lattice spacing. From, as I showed, about 400, 450 nanometer, I think all the way up to probably about 800 nanometer, 850 nanometer, very large range. So you can go to IR, you can get modes in the IR as well. So very good control over these parameters.
The next question is from Vishwapal. How to control coupling range between the elements in an array? Is it possible to achieve a mean field coupling? I think this is slightly similar to the previous questions, but yeah, that's the question.
Coupling is the question.
How do you control the coupling range between the elements in an array? Is it possible to achieve a mean field coupling?
Well, coupling range is essentially determined by the field. The individual plasmons generate a field, right? And then they are diffractively coupled. So you have to have the field due to the individual plasmon element being able to span the separation. So that is how the coupling will. If they are far apart, then they basically don't. They will not talk to each other. So there is no diffractive coupling. Okay. And so when you go to larger separation, then you have to tune the the resonance structures accordingly so that you can achieve a coupling that is a coupled lattice of metal discs. Even when the separation is, for example, 800 nanometer or something like that.
Okay. I don't see any more questions, Jadip. So I think we just crossed the time as well. And I would like to close the session. I would like to thank both the speakers for keeping their time and for giving us a fantastic session. Thank you very much. Jadip,
thank you.
Yeah.
Thank you.
Okay. So I think we will break now, right? And then
we break now and we reconvene at around 6 p.m. That's the poster session. and followed by the second session of this inaugural session.
Good. Excellent.